I hope it worked out with the coffee. So, as I already mentioned, I will spend some time now to speak about shape representation in general. So this is not with respect to shape optimization or topology optimization yet. This will then come in the next lecture. This is just a general introduction. And as already mentioned, I will focus on splines because they are important, first of all, because they're the basis of CAD programs. So that's why one should know about them. And also they're the basis, of course, of isogeometric analysis. So this is also why we need this. And then I will give an overview over some terminology in terms of optimization problems, what kind of optimization problems are there. And I will touch a bit on solution strategies. Of course, one can do a whole course on solution strategies of optimization problems, but yeah, I will mention a few things because this is also not our central topic. With these topics, I'm very sure that some of you are already familiar with it, some are not. I mean, this is the balance of that I have to strike here for such a course. So if you already know everything, just hang in there, and I hope that there's something for everyone. And that's at least what I tried to do. Okay, so how can we represent shapes? There's, in principle, explicit, implicit, and parametric shape representation. I will give the example for curves, but this extends then also to surfaces, volumes. So explicit curve representation means that I represent my y-coordinate as a function of the x-coordinate. So for example, if I have y is equal to the square root of 1 minus x squared, this will give me the unit circle, but only half of the unit circle. So it's a semicircle. The advantage of explicit curve representation is that it's very easy to evaluate. And it's very easy to analyze. So for example, if I have two curves, I want to compute the intersection, I can just equate the expressions. So that's very easy. It's axis dependent, and one cannot represent multiple valued functions. So for every x, there's only one y. That reduces the flexibility that we have. In implicit curve representation, we have a function of x and y, and the geometry is represented by the points where this function is 0. So if we look at the unit circle again, could be x squared plus y squared minus 1 is equal to 0. Now notice we can represent the full circle. So here, as the advantage that we gain is that now we can represent these multiple valued functions. However, we're still axis dependent, and also the curve cannot be computed directly. The touch again, it'll actually show. Then it always skips to. Okay. So, and geometry representation that we want to focus on, however, is the parametric curve representation. Let me go through everything on the slide. So here, the xy coordinate of each curve point is represented separately as an explicit function of an independent variable psi. So every coordinate on the curve can be computed using a function x of psi and a function y of psi. So we have this additional coordinate system that is connected to the curve. Goes around the curve. Usually we normalize psi, so then it would be between 0 and 1. So the unit circle could be obtained with such an expression, in which case psi is basically the angle. Here on the plus side, we have that it's extremely flexible. We can represent multiple valued functions, and we can also easily represent infinite derivatives. But on the minus side, some operations are more difficult. We already mentioned the intersections. This is difficult with parametric functions because the parametric coordinate system is then different for each curve. So it's harder to connect them. Or, for example, finding the distance from a point to a curve, or also specifying an unbounded geometry. However, an engineering component is generally not unbounded, so it really doesn't matter so much for us in this case. So let me tell you about one example for parametric representation. So while I write, let me sit. The Bezier curve has several components. So first of all, we need control points. And these control points, they guide our curve. So these would be the control points. P1. Why did it change color? Touch something. Okay, P2, P3, and P4. The control points are connected through the so-called control polygon. And those are just straight lines between the control points. This forms the control polygon. So here, these are the control points. This is the control polygon. And then the curve is guided by the control points, and it stays within the convex hull of the control polygon. And typical, or not typical, particular for Bezier curves is that they always interpolate the first and the last control point. This is always touched, but the others are not touched. They just guide the curve. How do we generate the curve? So the expression that we have to evaluate is that curve coordinates. So C vector are the curve coordinates as a function of the local parameter psi is equal to the sum over all control points. So from I is equal 1 to n of a basis function, BIP of psi times the control point coordinate. And here, the basis function, here we use Bernstein polynomials. Which are defined as follows. So we have an index I that, as you see in the sum, it's connected to the same index as the control point. So every control point has its own basis function. So this is this index I here. And then the P denotes the degree of this basis function. So it's a polynomial function of a certain degree. Psi is equal to n minus 1 factorial, n being the number of control points, divided by I minus 1 factorial times n minus I factorial times psi to the power I minus 1 times 1 minus psi to the power of n minus I. By the way, once the slides are uploaded, you will have all of this also in the slide in a more legible form. So they tried very hard to write legibly. In order to be able to evaluate this expression, we need several definitions. So this requires that psi is always in the interval between 0 and 1. It also requires that we define 0 to the power of 0 as 1. And we define 0 factorial also as 1. And the polynomial degree of this Bernstein polynomial, and through this also of the curve, is always n minus 1. So we have a strict connection between number of control points and degree of the curve. That's important for the Bernstein polynomials. I will wait for one moment until I go to the next slide, in case you're still writing. And then we can try it out, what's happening. So let's look at an example. So we can choose n is equal to 2. And we said that the degree is always n minus 1. So this means that the degree is going to be equal to 1. So for sure we will have a line segment. And we already see the line segment. And then we can compute the Bernstein polynomial. So we will have 2. So B 1, 1 of psi and B 2, 1 psi. So the first index again is the number of the basis function. The second one is the degree. So it's always 1 in this case. Now we can insert. So n is 2. So we have 2 minus 1 factorial. Here I is equal to 1. So we have 1 minus 1 factorial, and then 2 minus 1 factorial. So this leads us to 1 factorial divided by 0 factorial times 1 factorial times psi to the power of, so now we have to insert I minus 1. I is equal to 1. So psi to the power 0 times 1 minus psi to the power of n minus I, which is then 1. So we end up with 1 minus psi for the first basis function. Second basis function, now here I is equal to 2, and also n is equal to 2. So here we have n minus 1 again, so 1 factorial divided by 1 factorial times 0 factorial times psi to the power of I minus 1. I is 2 now, so psi to the power of 1 times 1 minus psi to the power of 0. So we end up with psi for the second basis function. So the curve is then evaluated as 1 minus psi times the coordinate of the first control point plus psi times the coordinate of the second control point. And then if we insert values between 0 and 1 into this expression, we obtain the coordinates of the curve as they're shown here. And notice that in this case here, I mean, I've not specified it, but it's sort of implied that here we're in an XY coordinate system for our curve. And this is why we have vector values for the curve and also for the control points. But the local parameter psi, that's a scalar. It's a curve, so we only have one parameter. And this is called an immersion, meaning that this curve is embedded in a higher dimensional space. Which later, when Matthias will speak about isogeometric analysis, you will see that that makes your life more complicated because it makes, for example, integrals harder to compute because of these immersions. Okay. For completeness, we can look a bit more quickly at a second example, the quadratic Bézier curve. So now n is equal to 3, meaning that p is equal to 2. So then we have 3 basis functions that we need to compute, B1, 2, B2, 2, and B3, 2. Or we can go through this a bit more quickly. So here, now n is equal to 3. In the first case, I is equal to 1. So we obtain 2 factorial divided by 0 factorial and 2 factorial times psi to the power of 0 and 1 minus psi squared. So in the end, we end up with 1 minus psi squared as a basis function. Then for B22, we have 2 factorial divided by 1 factorial times 1 factorial times psi to the power of 1 and 1 minus psi to the power of 1. So now for the first time, both expressions actually play a role. Then our basis function is 2 psi times 1 minus psi. And then for the last basis function, 2 factorial divided by 2 factorial times 0 factorial times psi squared and 1 minus psi to the power of 0. So the basis function is psi squared. And our curve phi of psi is then computed as first basis function times coordinates of the first control point plus second basis function times coordinates of second control point plus the third basis functions times the coordinates of the third control point. So this is the Bezier curve. This is one example of what this quadratic Bezier curve is like. But depending on how we arrange the control points, we can represent many different shapes. If we go to cubic, for example, we have 4 basis functions in total. And here on the right, you see some examples of what curves look like depending on how we arrange the control points. And notice if we plot the basis functions, that the first one takes on the value of 1 at psi is equal to 0. And it's 0 at psi is equal to 1, just like the orange one and the red one. And this is, and then here at psi is equal to 1, the green one is 1, and everything else is 0. And this is why the first and the last control point are actually interpolated, because only the first control point plays a role for the shape of the curve due to the property of the basis function here. We can continue to quartic. The picture is very similar. So again, here only the first basis function has the value of 1. All of the other ones are 0. And we can generate a curve that looks like this. And here I want to give you an example for another property. So all of the basis functions are non-zero everywhere in the domain except for these 2 boundary points. This means that if I shift one of the control points, I will affect the whole curve everywhere. So here I shifted just control point number 5, and we changed the curve shape everywhere. I mean, here it's not super visible, but in principle, we changed it everywhere. And this is the problem with the Bezier splines that were the first type of splines that were used, that we do not have the local control available because of the property of the basis functions. This extends to surfaces, this whole idea. If I want to represent a surface, then I need 2 local parameters, one for each direction of the surface. So then I have 2 local 2 basis functions, and I have a control point grid. So now we have a double sum. So this has to be a structured grid of control points. And those basis functions are simply the univariate basis functions of using one of these parameters. So it's a tensor product structure of the 1D Bezier splines, the surface. So if we summarize, let me go through everything. So the properties. The curve is contained in the convex hull of the control polygon. And the convex hull is the largest convex polygon that we can generate using the control points. So the curve will always be in there somehow. And the control points guide the shape. And the basis functions are real and non-zero throughout the entire definition space. We already said the curve touches, meaning interpolates the first and last control point. And the Bernstein polynomials form a partition of unity. There's some drawbacks to Bezier splines. So the control is not sufficiently local. The reason being that the Bezier curve is a single segment curve. And this means that a high degree is required to satisfy a large number of constraints. So if I have complex shapes, I need more control points to represent this. This automatically means that I need a high degree because there's this direct connection. So this is a drawback. And then the second one didn't want to show up. There's a second main drawback. Namely, I'll just tell you. So there's important types of curves that cannot be represented using Bezier splines because we have polynomial basis functions, so we cannot represent conic sections. So no circles, spheres, cylinders, all of these things, which in turn are very important in engineering. We saw, for example, we don't want the stress concentration, so we want a radius. Now with the Bezier spline, we cannot represent the radius because it's based on polynomials. So this is why they're no longer used in CAD systems. So first improvement over Bezier splines are the B-splines. B-splines are essentially structured in the same way. I'm just going through everything here. So we have the curve that is a function of a local parameter xi. We have the sum over all control points. We have control point coordinates, and we have basis functions. So what we change now with respect to the Bezier curves are simply the basis functions. We use different basis functions, no longer the Bernstein polynomial, but the B-spline basis functions. Again, we have an index here, so every control point has its own basis function, and we have a degree of this basis function. Now, one difference is that the degree is no longer connected to the number of control points. So now I can choose the degree freely. So what is special about the B-spline basis functions? They're computed using the Cox-de Boer recurrence formula, which is easier to explain in a picture, I think. So we start with constant basis functions. So first we define constant basis functions. Through the constant basis functions, we can then move to linear and then to quadratic and so on, however high we want to go. So this is why it's called a recurrence formula. So this is the definition space of psi. So here it's between 1 and 6. It is, I said that usually we're normalized. It should be between 0 and 1, but we don't have to. So here it's between 1 and 6. And we choose breakpoints in our domain that are called knots. And these knots tell us where a constant basis function starts and ends in the sense where it takes on the value of 1 and everywhere else it's 0. So the first basis function takes on the value of 1 between the first two knot values, so between 1 and 2, and this is called a knot span. Now the second basis function is 1 between 2 and 3 and 0 everywhere else. So we go on like this. And then we take two of the constant basis functions and we combine them to a linear basis function. And we combine them using this expression here. So you see we have two basis functions of degree p minus 1, so of a lower degree, that we combine. And we have these terms here that elevate the degree. So we go from constant to linear. And this red curve here, the red constant basis function is responsible for this first part, and the blue is responsible for the second part. And then we can continue. We can take two linear ones and combine them to form a quadratic one. And we get this type of quadratic function. What do I want to say? Yeah. So the colors tell us how the constant basis functions propagate through to those quadratic basis functions. So we still have the red one that kind of is originally responsible for this first part here, the blue one that is responsible for this part. And this means that the basis functions are only non-zero in a certain portion of our domain for psi. And this is what will allow us local control, that the basis functions are non-zero only in a small part, in particular in p plus 1 non-space. Also, this extends to, was there a question? So, yeah.
Except for the 0, there is an overlap, right? So the control is local, but it's not exactly, let's say, one-to-one. If I move a control point, I will also affect something not related just to that this function.
Well, also, well, here we always have an overlap. So for linear, we have two basis functions that overlap in each knot span. So for degree 0, we don't have any overlap at all. And I don't think it's even possible to form a curve like that. No. Because if it's degree 1, we replicate the control polygon. If it's degree 0, it is nothing. It's some disjoint structure.
G.
It's DG.
G. Or finite volumes.
Yeah, well, if you think about it, so sorry, I need to repeat for the online community. So the original question was about the overlap of the functions, which is always p plus 1. There's a magical number. So for B-splines, so every basis function is non-zero in p plus 1 knot spans, and in every knot span, p plus 1 basis functions are non-zero. So you can remember p plus 1 as a magic number. And then Matthias was commenting that if we use only use constant basis functions in an isogeometric analysis context, that would be discontinuous Galerkin. But we've not even spoken about isogeometric analysis. So. Also here, we can extend the concept to surfaces and also to volumes. So for the volume, then, because we already saw the surface, we need 3 local parameters. We have 3 univariate basis functions that we combine in a tensor-like fashion. Here we have a control grid with the 3 indices now. And then we can also generate spline volumes. And this whole idea also extends to higher dimensions if you have use for that for some reason. So also here, let me summarize B-splines. So also here, curve is contained in the convex hull of the control polygon. Also here, basis functions are real and non-zero. Local control is now possible. We have a partition of unity. Local control is no longer a drawback, so we resolved one problem here, but important types of curves cannot be represented still because we still have the polynomial basis functions. So that brings us to the last type of spline that we want to talk about, the NURBS. So actually, these spline types are generalizations of each other. So every Bézier curve can also be expressed as a B-spline. And when we talk about NURBS now, that will come here, every B-spline can also be expressed as a NURBS. So those are generalizations of each other. And we said that we still have this drawback that B-splines cannot represent conic sections because polynomials cannot, but if polynomials cannot, what can maybe? So how can we improve the situation? Let's do this thought experiment. We have the unit circle here, and now we generate lines that go through this point -1, 0 here. And then we record the intersection of this line with the y-axis. So we have some points here that we parameterize as 0t that are intersection with the y-axis. And of course, also we have the intersection point here available. So those blue curves can be expressed as y is equal to t times x plus t, because we have the slope. Just by definition, we have a rise of t and we have a run of 1. So the slope is going to be t, and the intersection with the y-axis is going to be t. And if we compute the intersection point with the unit circle, for the unit circle, we have the expression y is equal to square root of 1 minus x squared. So now we compute the intersection, and we obtain x is equal to 1 minus t squared times divided by t squared plus 1. And y is equal to 2t divided by t squared plus 1. So what we wrote here would be a new way of parameterizing the circle, because now we can reach all of these points on the circle also using this expression as we're using this parameter t that we previously recorded. And what we see here is that we have rational polynomials. So we have this denominator of t squared plus 1 in both cases. So polynomials cannot represent a circle, but rational polynomials can. And this is the idea of NURBS, that now we have rational polynomials as basis functions. So NURBS are our solution. So waiting for the spline. So what are NURBS? NURBS is an acronym for non-uniform rational B-splines. So we already see it's somehow connected to B-splines. So we reuse the B-spline basis functions in some way. Rational because we have a rational basis, so ratio of two polynomials. And non-uniform because we have a non-uniform knot vector. Remember with the B-splines, I told you about the knots, which are the breakpoints that tell us where the constant basis functions are defined. In our example that we saw previously, that was equally spaced, but it doesn't have to be equally spaced. So this is why, and then it's called non-uniform. So this is how the name of non-uniform rational B-splines comes about. Or in short, NURBS. Um, so also for the nerves, we have the structure first. Look here, only at this part. So we have the curve as the function of a local parameter, and we have a basis function times control point. That always stays the same. Now, in our case, because we want this rational polynomial, this basis function looks like this. We have the B-spline basis function, NIP, times a weight. And then in the denominator, we have the sum over all of the basis functions times their weights. So this is how we get this rational structure. And one can also just plug this in and then write it directly, but I find it easier to see if we have the same structure, basis function times control point coordinate. If we do it that way, of course, continuity and support of basis functions follow from the not vector. Also, R constitutes a partition of unity. R is non-negative. Weights and coordinates of control points can be chosen independently. And if all weights are equal, then this basis function R is equal to the B-spline basis function, because if all weights are equal, we can take this out of the sum. Then we have the partition of unity property that tells us that the sum over all B-spline basis functions will be 1. So we have the weight divided by the weight, and we obtain this n. So then this is what I meant. Every B-spline can also be expressed as a NURBS if all weights are chosen equal. What does the weight do? Depending on the weight of a control point, we can increase the influence of this control point on the shape of the curve. So here we see an example where the weight of control point 2 is 0, so then it has no influence on the curve at all. We increase the weight and the curve moves closer to this control point. So it's very intuitive. Oops. So that you don't fall asleep, I have a little quiz for you. You would need to go to this link. So polleverywhere.com, then my name 718. And this will give you a poll that hopefully allows you to answer this question. Let me quickly check whether this is activated. And then I will go back to the slide so you can actually see the question. Okay, activate. Okay. So I have 3 NURBS curves here, and I have 3 basis functions, and they're mixed up. So the question is now, which basis function corresponds to which curve? Of course, I can repeat the question. So we have 3 NURBS curves here that we see. So this in black is always the curve, and then in gray is the control polygon. And then we have 3 basis functions, 3 sets of basis functions. And basis function set A does not correspond to this curve, but it corresponds to some other curve. So the question is to sort basis functions and curves. Yeah, I can try to zoom in, maybe. Has someone managed to access the link? Is it working? Okay, good. All right, so I will show the question again just briefly, and then I will go to the website and we can see what the answers are. The pole is full. Oh, I didn't realize that there's a limit. I'm sorry. Okay, but I guess then we can evaluate. No one else will be able to answer. So what is the? Okay. So 64% of people say that curve A goes with basis C, curve B goes with basis A, and curve C with basis B. So we can check that's true. So let's start with this case. So here, the basis functions never touch the value of 1. So we do not have this feature that we saw with the Bezier curves, that the first and the last basis function actually reaches the value of 1. So this means that the first and last control point will not be interpolated. So this is true for curve B. Then here, for this set of basis functions, this is the case. So we're looking for something that interpolates the first and last basis function. And so this will eventually correspond to curve B, which we can know, let's say, once we look at basis C, we can deduce that this is connected to this curve, because the circle is usually comprised of a number of circular arcs that are connected, either 3 or 4. In this case, it's 3 circular arcs, and we can still see the structure of those circular arcs here. So here we touch a control point, and here we also touch a control point. So overall, we should be interpolating 1, 2, 3, 4 control points. We obviously see 3, and then 1 control point is actually overlapping because we closed the curve. So this is how we know that this base is connected to this curve, and then basically this is what is left over, but also makes sense. So very good. Okay. Yes, please.
So how many degrees of freedom do we have in the end to describe fully this curve? So we have the control points and the weights for each control point, and then we select that's it.
So the question was how many degrees of freedom we have in these curves, and basically the participant already answered the question. So we have the coordinates that we can adjust, and we have the weights that we can adjust. And of course, like previously, we already made a selection about our knot vector, so where we place the knots, and this influences the basis function, and then of course also influences the properties of the curve. But once we have this curve available, it's easiest to modify the control point position if we want to change something. So let me speak about categories of optimization problems. This is basically about terminology. So we can differentiate between discrete optimization and continuous optimization. If we think about discrete optimization, then our optimization parameters can only be selected from a discrete set. So this is, for example, the case if our optimization parameters can only occur as integers. So for example, if we look at the number gas stations in a city, this would be an example of discrete optimization, how we want to place them optimally. However, this can also mean that we look at permutations. So I mentioned I studied manufacturing engineering. So in extrusion, we have these screws that transport polymer, and you assemble these screws from different base components that you can see here. And also how to put together these base components could be an example of a discrete optimization. And this problem class is also called integer programming. Instead, in continuous optimization, our optimization parameters are chosen from a non-countable infinite set, and this is called continuous programming. And there's also a combination of both then called mixed integer programming. And we will concern ourselves with continuous optimization. So shape optimization would usually be a continuous optimization. Then we can look at linear programming or nonlinear programming. Linear programming means that the objective function and all constraints are linear functions. This is very typical for financial mathematics or business administration. Instead, in nonlinear programming, either the objective function or at least one of the constraints are nonlinear, and this is very typical for natural and engineering sciences. So we are here on the side of nonlinear programming. Then we can try to seek a global optimum or a local optimum. So for a global optimum, the value of the objective function for a given value of the optimization parameters has the smallest achievable value within the solution set, U admissible. So the definition is that the value at this global optimum is less than or equal to all other values within the admissible set. Instead, for local optimum, the value of the objective function for a given value of the optimization parameters is smaller than in the immediate environment. And here's an illustration. So this function here has several local optima. So all of these points here are local optima, and this here is a local and a global optima. And yeah, the problem is, or will be, that if we start to search somewhere for an optimum, we can easily get stuck in a local optimum. So this will be the challenge. Then I want to speak about the difference between shape optimization and topology optimization. In shape optimization, we already fixed the basic layout of our domain. So in our cow example, we had this sheet of paper, and this was already fixed as a layout. And then I was able to fold it or crumble it, but the layout itself was fixed. So we can adjust the boundaries. And this means that the initial geometry and the optimal geometry that we compute somehow can be transferred into each other using a continuous mapping. So in particular, the subsequent insertion of holes is not possible. So the picture I showed you where then I cut holes into the structure, this is not possible in shape optimization. The holes would need to be there beforehand, then I can adjust them, but I cannot insert them. Instead, topology optimization actually concerns itself with defining this basic layout. So it's not so much about finding the shape, but about distribution of material. And we want to find the optimal load path. So wherever our forces want to be transmitted, this is where we want to put material. So as such, it's the most general type of structural optimization that you can think of. Usually, it is used to find the lowest amount of material input that we can use in order to still have a functioning structure. And it became even more popular than before because of recent breakthroughs in manufacturing technology, in particular in terms of additive manufacturing, where one can then actually manufacture those very let's say, innovative shapes that come out of topology optimization. If we look at some pictures, so these are trusses. This would be an initial design. In shape optimization, we can just modify the shape of this truss. so the size or the shape, but the number of beams here is fixed. Whereas in topology optimization, I have some initial number here, and then I can actually remove some of the beams. Or more general, in for complete structure, it really teaches you patience, this course here. But sometimes it works well and then it gets stuck. I don't know. Here it is. So in shape optimization, this could be an initial design. For example, we already decided for 3 holes, and then we just kind of adjust the shape of these holes, whereas in topology optimization, the initial design is just a very big domain, and then those holes sort of appear throughout the optimization. And often both of these approaches are mixed. So we use topology optimization to kind of determine the layout. And then we can use shape optimization for local adjustments. In particular, because what comes out of topology optimization is sometimes not ideal in terms of manufacturing it, or the shape is usually not very smooth. So then the shape optimization can be used for some fine-tuning. We spoke about global optima and local optima, and for sure we will run into several local optima, but in topology optimization, there's even a very simple example with multiple global optima. So this is the definition of the load case. So we have a line load Q. Our design space is screen space here. And this solution has exactly the same stiffness. So this problem of having many different optima and which direction we walk into is very present. And this is also why one needs to take really good care of what does the objective function look like, what we said in the beginning. Hey. Let's talk about some solution strategies. So how can I recognize the local minimum? And now we want to find some strategy how to get there without computing the entire objective function. We only have certain number of evaluations of objective functions that we can afford. Well, if an objective function is sufficiently smooth, then the local minimum can be identified by analyzing the gradient vector and the Hessian matrix. So we have the necessary condition that if omega star is a local optimum for objective function j, then the gradient of j is equal to 0 at omega star. And furthermore, we have the sufficient condition that the Hessian is positive semi-definite at this point. This is for the local optimum. For the global optimum, we don't even recognize it if we're sitting in it, because the only definition of the global optimum that we have is that the value there is lower than all objective function values everywhere else. So there's no means of knowing if we're in a global optimum or not. And then we said we always have a constraint. So we have an objective function that is, for example, minimizing the compliance or some deflection or something. But we said we want the solution to also comply with the physics. But we also want the solution to satisfy, let's say, the linear elasticity structural model. So this is our constraint, which is an equality constraint. So I wanted to briefly look into how we can solve optimization problems with an equality constraint. So for now, this is not a PDE yet, our constraint, but it's just some function, and also our design variable is a scalar value. And our solution variable is also a scalar value. But in practice, our design variable would be some kind of shape parameter, and the solution variable would, for example, be the displacement field of our structure. So these are the two equations that we're using here. This is the constraint then. So these are contour lines of the objective function. We can see that this would be the minimum, but we also want to satisfy the constraint. So actually the solution that we're looking for is here. And notice that the solution, at least optically, we can sort of see this, is characterized by the fact that the gradient of the constraint, this is where the constraint is equal to 0. Gradient will go somewhere up here. The gradient of the constraint and the gradient of the objective function, so the contour lines, they point in the same direction. And this will be useful for solving this problem. This point doesn't care to appear. There it is. Okay. Oops. So, example. So we have j of d and u that we now define as d squared plus 2 times u squared, and as the equality constraint, d of d and u, we use 2d minus u minus 9. So this doesn't have any particular meaning. It's just random, more or less. So how could we find the minimum now? Well, since these are scalar variables, we can actually use the equality constraint to express u in terms of d. So for every configuration, or for every value of the decision variable, we can directly compute u. So we could say that u is equal to 2d minus 9. So later, this will mean that we're solving a partial differential equation. This is in our picture with the forward simulation. We put in a certain geometrical configuration, so certain d, and we obtain the displacement field, for example. This is exactly the same procedure. Then in a second or not connected step, we can compute the gradient of the objective function with respect to the decision variable. So this would be 2d plus 4u times the derivative, of u with respect to d. We already have this expression for u, so du dd is equal to 2, so we can plug this in. So then 2d plus 8u. So we continue with 2d plus 8u, and then we plug in our expression for u. So we end up with 18d minus 72 for the derivative of j with respect to d. Now we know that this should be 0 at the optimum. So we have 0 is equal to 18d minus 72. So d is equal to 72 over 18, or 4. This would be the optimal value. So why did we do that? Mainly to see that here, through the constraint, we get a relation between d and u. We need the gradient of the objective function with respect to the decision variable. And we can, so this expression then also contains du dd, which we can obtain from here. So this is what will help us to solve this, and this is also later what will help us to solve it in a PDE scenario. But now we stay with the scalar variables for now. So we are searching for the minimum of j of d and u, and we have this equality constraint, and we could perform forward sensitivity analysis. So for fixed d, the constraint equation can be solved for unique u. We just did that. And then in order to perform the optimization, we need the gradient of j with respect to d. So this is also what we just computed in the example. And now in the general case, how do we obtain du dd? That is the question. And so we compute the derivative of the equality constraint, so dc dd. So here we have this first term that is the partial derivative of c with respect to d, and then we have the partial derivative of c with respect to u times the inner derivative, and this can be, here we can then solve for du dd. Then we get this inverse here, which in the scalar case is very easy to compute, but then later we will have to deal with matrices. And then we can insert this back into the objective function, and this is how we can compute the gradient of the objective function with respect to the decision variables. Instead, we can also use the Lagrange function. So we formulate the Lagrange function with a Lagrange multiplier lambda. So now we have this Lagrange function that is not only a function of u and d, but also of the Lagrange multiplier lambda. And then we have the objective function minus lambda times c, so times the equality constraint. And then it is known that the minimum that we're looking for coincides with the saddle point of the Lagrange function. So with all partial derivatives of the Lagrange function being equal to 0. And this is why I mentioned this fact with the gradient of c and the gradient of j, they have to align. They have to be in the same direction, but they can have different value. If we look at this, this is exactly what the Lagrange function gives us, and we have the lambda that lets us adjust the magnitude of these vectors. So we look at the same example that we just computed, then this will lead to the following Lagrange function. So we have the objective function, and here we insert the equality constraint times the Lagrange multiplier. So then we're looking for the saddle point. So we can compute these partial derivatives of this function that will give us those expressions. So from this equation, we can then compute that lambda is equal to d. This equation gives us an expression for u. And the last equation then lets us compute a value for d. So also here we would obtain d is equal to 4, just like we did before. So this is how the Lagrange function would work. In the general case, we have, again, the saddle point, so these three partial derivatives. And notice that this first equation, this ensures that the equality constraint is fulfilled. So we do have the minus here, but it still ensures that c is equal to 0. And, oops. Oh, there's a question.
They basically are saying that the gradient of j and the gradient of c are parallel, correct?
Yes, exactly. So here Yeah, so this is what ensures that the gradients are parallel, as we just said. So here, as an overview, constraint is fulfilled. Second equation is used to identify the Lagrange multiplier, the value of the Lagrange multiplier. And then the third equation is used to compute the derivative. So whatever we have here, we can insert it here, and then we can compute the derivative. So we always have these three steps: constraint, Lagrange multiplier, derivative. So in a shape optimization example, look at an airfoil. D could be the boundary coordinates of our airfoil. U is the velocity field. So this is our solution variable. So we have decision variables D, so the shape. And we have solution variables U, which is the velocity field. And those two are combined in order to find a relation between the shape and the drag in this case. So this could be our objective, that we want to minimize the drag of this airfoil. So these two are now connected using a PDE simulation. So we solve for the flow. That gives us the relation between D and U. And from whatever we have, we can compute our objective function, which takes D and U and then gives us the drag. So both variables enter into our objective function. And then in our optimization procedure, we want to minimize the drag under this condition that C is equal to 0. There are several methods for determining the gradient. We already saw some options. We can work on the level of the continuous differential equation, and we can try to compute the continuous adjoint, so we can try to compute gradients on a continuous level. Or we perform the discretization, and then we compute gradients on a discrete level. Or if we are already past that step, we've already implemented something, and we then have the program source code maybe available, we could use algorithmic differentiation to differentiate the source code, and that could give us the gradient. Or if we don't have access to the source code, it's already compiled and we only have the executable program, then we're basically left with finite differences as an option. So it really depends where we can start the process of trying to determine the gradient, what would be a good method. And I wanted to focus on discrete adjoint methods. So we already saw the derivative of the objective function. Saw it several times now. We have this du dd that we need to compute, that we can obtain from the constraint. So then the gradient can be computed using this expression. And this can be evaluated in either forward sensitivity analysis or adjoint sensitivity analysis. In forward sensitivity analysis, we have exactly the equation that I just showed you. And here indicated is, as an example, the size of the underlying vectors. So here we have a scalar objective function, and we have a certain number of decision variables. Again, the same thing here. We usually have more solution variables than decision variables. So if you think about the airfoil has maybe a handful of geometrical parameters, but the finite element mesh for the flow solution would have many, many nodes. This is why this vector is longer. Then we have always a square matrix of dc du, and we have another matrix, dc dd, where again we reflect sort of the fact that we have fewer decision variables than solution variables. And if we want to try to solve this, which we for sure can, we have this inverse matrix here. This would require us to solve n linear systems. So this is a big effort, which can be changed easily if we take the transpose and then come to adjoint sensitivity analysis. So down here at the bottom, we have exactly the same thing, just transpose of everything. And then this reduces to one solution of a linear system. So it's always advisable to use this version here. Then instead, if we want to go with the Lagrange function, so the discrete Lagrange function, in this case, again, solution is the saddle point. We have the same equations as before, and they're also should be color-coded nicely. So the green one gives us the constraint. The red one gives us the Lagrange multiplier. It's called the adjoint equation. And this will give us the gradient. And if we put this into an implementation, so we would take some guess of our decision variable. We start with some initial shape. We solve our constraint equation, so finite element simulation. And this already will contain this a partial derivative of C with respect to U. So we already need the Jacobian for the solution of this, which we can then reuse in the adjoint equation in order to solve for lambda. And then we can plug it into the gradient. And once we have the gradient, we can use some optimization method, for example, steepest descent, Newton, whatever we prefer, to find a new guess for D. And then we iterate. So as an illustration, now back to the scalar variables with the steepest descent. We start somewhere. We make a decision update based on the adjoint solution that will bring us away from the constraint. Then we solve the constraint equation to come back to the constraint. We compute the gradient again to make another decision update. Brings us away from the constraint. We go back by solving the constraint equation, and as such, we continue. And after roughly 50 iterations, we're very close to the optimum. All right, that concludes the second lecture. That was incredibly too long. So we spoke about, it doesn't matter because we have some buffer in the end. We spoke about methods of shape representation, so explicit, implicit, and parametric. We spoke about Bézier splines, B-splines, and non-uniform rational B-splines, so where the difference is basically local control and the conic sections. And we spoke about solution strategies for optimization problems, so we can analyze the gradient and the Hessian in order to see whether we're at an optimum, and adjoint methods can be used to compute the gradient. In the, I guess according to the program, I still have 15 minutes, but I will start with what I thought would be lecture 3. And then we can continue after lunch. So now I would like to speak about geometry representation in shape optimization. So we already spoke about the splines, but then how does this work in a shape optimization context? I would like to speak about geometry representation in topology optimization. How can we find these layouts? And I would like to summarize some objective functions in topology optimization. Let's start with the shape optimization. So now we're talking, if we think about our loop, we're talking about parametrization. So in principle, we have two options how to represent shapes. This can be parameter-based or parameter-free. In the parameter-based case, our geometry omega is described using general parameters. These can be very simple geometrical parameters like height of some square or something, or it can, for example, be spline-based, which lets us represent more complex shapes. In the parameter-free case, omega is described using a computational mesh. So probably we already have some kind of finite element, finite volume, or something mesh for our solution. So we use that also to describe the geometry. Of course, one can argue whether this is really parameter free because the coordinates of the nodes will then be the parameters, but there's no reduced parameter set. This also means because we have these many parameters that this is really prone to oscillations. So you will need to perform some kind of filtering in order to obtain a smooth shape. So if we go through advantages and disadvantages of the different approaches. So here we only have very few parameters, but also we have a low variability. With the splines, we can represent complex yet smooth shapes. We have a high but still controlled variability. We CAD conform. That's very good because then whatever is our optimization result can be reintroduced into a CAD CAM manufacturing process immediately. But we still have a predefined parameter space. So with the choice of spline, we also make a choice of our admissible set of shapes. Here we don't have that. We can basically represent any kind of shape. So we have the highest possible variability. This high number of parameters will require advanced optimization algorithms. We're not CAD compatible. So afterwards, we need some kind of fitting in order to come back to the CAD system. And of course, there's the question of the smoothing and how you do the smoothing. If we look at the splines, then we basically have two options how we can use that in shape representation. So we can use the spline representation directly. So this is a surface representation of an extrusion die. We can, and the control points are what is deformed in order to obtain new shapes. Instead, here is the so-called freeform deformation. There's a video that should play. So we take our structure, we embed it into a box volume spline, and then all of the surface points are connected to the spline, and as the spline deforms, also the surface deforms. And I will show you how it works exactly in a bit. So first, the boundary representation. So we use that for shape optimization of extrusion dies. For example, here you have the problem that you want the velocity of the melt at the outflow to be as homogeneous as possible. And here we have the velocity, and we see that for this L profile, this leg, the velocity is much higher than here. So one wants to adjust this. And so this is the optimal result then, where we see that here the cross section is much bigger now. So this leg was sort of opened up, and there's some kind of structure that is inserted between those two legs. And why did it happen exactly like this? Because we talked to practitioners and we asked them, what would you do? And they told us that basically they have three kind of measures that they would take. So first of all, they would adjust the slope here of these legs. They would create something that we call nose, so a structure that prevents cross flow between the two legs, and something that we call bone, which is this bone-like shape that is created here, where because of the wall adhesion, the material is slower. So you want to get more material into these edges where there's higher wall adhesion. And the control point color coding reflects exactly these design features. So the red control points are all connected to adjust the slope. They cannot move freely. They all move together and they will adjust the slope. Those orange control points, they will form this bone. So overall, we only had 7 design parameters. So the admissible set of shapes was rather limited and was basically a sizing of these different features that we performed during the optimization. For the freeform deformation, the idea of freeform deformation is already quite old. So the first paper was published in 1986. From computer graphics, and the idea is that you embed shapes, here the circle and these cubes, into some outer shape. So here there's also a cube, and you deform the cube, and automatically also these shapes in the middle adjust to this. So the way it is used in shape optimization is a bit different from the original idea. You take a box spline, so here this rectangle, and you embed a point cloud, which describes a certain shape, and then as you deform the box spline, also those points deform. And how does it work? So of course they need to be connected to the spline. So here's a video. You have the finite element mesh, you embed it in the spline. Then if you change one of the control point positions, the finite element mesh will also be modified. So the procedure. First, we have the embedding step. Let me go through all of this. So we want to connect the point cloud with the box spline. So one option would be that I select the spline in such a way that the local coordinates of the spline correspond exactly to the global coordinates of these embedded points. So whatever are their XY coordinates, those will be the local coordinates of my spline. This is very easy to generate. If I don't want that, I want a spline that is normalized, for example, then I can solve an optimization problem. It gives me the shortest distance of one of those orange points to the point on the spline surface, and then gives me the local coordinate that is in any case, what I get out of this embedding step is the connection between every point and a local coordinate on the spline. This makes the deformation step very easy, because then I just evaluate the spline at all of those local coordinates, and I get the new positions of my points. So this is what is called freeform deformation. And then if we look at the node-based geometrical deformation, here I had to borrow from some papers, because this is something that personally I do not do, but it's very important, so I wanted to mention it anyways. So here is an example where one wants to find the optimal shape of this hole. So you have a plate with a hole, you have a certain load here, and you see that for a while it does very well, but then there's these oscillations that occur, which are numerical artifacts basically related to the fact that these creases increase the stiffness, and the optimizer finds that favorable. So you want to smooth this out, and there's many very, very sophisticated ways of how to smooth this, but you can also do it in a very simple way. To obtain a new nodal coordinate, you average the nodal coordinates of neighboring points. So this will sort of adjust the displacement of neighboring nodes to each other and average it out. But this is just one example. There's many, many much more sophisticated ways of doing that. There's, of course, a parameter that sort of controls the intensity of the smoothing. Then you have to somehow determine this parameter, like any parameter. This causes some, either you can say it causes some complication, or it gives you additional freedom, whatever you prefer, whether you're glass half full or glass half empty type of person. You can also do several smoothing runs, so several filter passes to enhance the filtering. So with this approach, a lot of the smoothing and how you do the smoothing will tell you which local optimum you will go into. So the idea is that you use many different smoothing techniques in order to explore many different local optima to see which kind of shape is the one that you would find preferable. Okay, let's see. So now in theory, I have 4 more minutes. I'm trying to decide whether I should start. Yeah, I will start. Just So geometry representation in topology optimization. So again, we're speaking about the parametrization of the geometry. If we look at the topology optimization procedure, then first we have to define the design domain. So here, as an example, there's the floor of this airplane. There's a certain load, and this could be our design domain in green. We define the loads and the boundary conditions, and then we perform a discretization of our design domain, for example, with finite elements. And then we iteratively find the solution of our optimization problem, and we end with post-processing and the final design proposal. This is the general idea. There's many types of parametrization. So we already had this example with the trusses, so discrete structures as opposed to continuum structures. So we would like to go down this path of continuum structures. Then you can have some approaches connected to the macrostructure that we will not talk about, or microstructured approaches where you modify the material according to the load path. So here you have design variables that are connected to these discrete elements or whatever you have here. And this can either be discrete, so you can have elements that are active or not active, or it can be continuous, where you have some kind of continuous field that tells you where do we have material and where do we not have material. And what is already mentioned here, this SIMP is the most popular method. So this is a continuous design variable. So so as an example of a continuous design variable, we have a material model which has a certain density. And this density can cover a range from 0, which means that the cell is empty, through intermediate values to 1. So intermediate values, one could say that this is connected to composite materials, but you could never manufacture intermediate values. So if we want to try to represent this lamp example, then we would have cells here that have a value of 1, so they're completely full with material. We have some intermediate cells here. So this is roughly what would give us the lamp. This is the idea. We have the advantage that inherently this already provides a regularization of the topology optimization problem, because we have this continuous field. So this is related to the well-posedness of the problem. And the approaches, the exact approaches differ in how these intermediate densities are treated in the end. And then in the homogenization approach, the design domain is filled with a porous material. So each cell has a certain porosity, and then you adjust the porosity. Whereas in the solid isotropic material with penalization, or SIMP, that we already saw, we use an isotropic material, and we adjust the density. And this, I guess, is what we will do after lunch. So I will show you how it works to use SIMP in the density approach. So according to the program, we continue at 2 o'clock. I think everyone who's here in Udine can now head to the restaurant. Everyone at home has to find their own lunch, unfortunately. So I will see you again at 2 o'clock. Thank you very much.